So next I want to introduce Ben and Jany. We're talking about q-Matroids and rank metric codes.
Okay, cool. Thank you, Caitlin, and thank you all for being here. Yeah, so today, as my title says, I'll be talking about q-Matroids and rank metric codes. So let me first explain a little bit what those two terms are. And let me get that spotlight thing. Okay, can you see that spotlight? Okay, cool. Okay, so let's start with q-Matroids. So q-Matroid was defined by Crapo in the 60s, and afterwards no one ever did anything with it, and so it was rediscovered in 2018 by Urias and Pelican. And what this q-Matroid is, as you can kind of guess from this little q in front, q-Matroids are just the q analogs of matroids. Okay, so it's kind of a new theory. And the goal of those q-Matroids, similar to matroids, is to try to find mathematical objects out there that induce a q-Matroid, and that hopefully that q-Matroid will kind of extract useful information from those objects, right? And so Urias and Pelican defined those q-Matroids from those rank metric codes. And those rank metric codes are some objects, so they're subspaces of a finite dimensional vector space over a finite field associated with this rank metric, and they're really useful in coding theory. So I won't go into the details, but just know that they're really useful for coding theory, and so we want to know more about those rank metric codes. Okay, so let me go into the actual definition of a q-Matroid. So Urias and Pelican defined a q-Matroid from a rank function. So this rank function is a function from the collection of subspaces of fq to the n to the integers. And here fq is the finite field of order q, okay? And this function rho needs to satisfy three properties. It needs to satisfy some boundedness properties. So for any subspace v of fq to the n, rho v must be between 0 and the dimension of v. It has to satisfy a non-decreasing property. So if I take two spaces v contained in w, the rho v is less or equal to rho of w. And the last property this rho function needs to satisfy is this submodularity property, where if I take any two spaces v and w, the rho of the sum plus the rho of the intersection must be less or equal to rho v plus rho of w. Okay, if we have this rho function that satisfies all those properties, we call the pair fq to the n rho a q-Matroid, and rho is the rank function of that q-Matroid. So using that terminology, I'll also often, or I might say that this rho v is just the rank of v, okay? And this is really, it seems like really the q analog of a matroid, because we define this q-Matroid from, or this rank function from the collection of subspaces. And if you know about matroid, you know that the rank function of a matroid is defined from the power set of a set 1 through n. So it really has this q analog feeling to it here, okay? So as I mentioned before, those q-Matroid, we want to extract information from different objects. And so I will introduce now those fq to the m rank metric code, which I'll just use rank metric code and kind of delete this fq to the m just for be a little smooth. Okay, so before clearly defining those rank metric code, let's first start with this rank metric. So the rank metric is just a metric on the space fq to the m to the n. Okay, and to define this rank metric, what we first need to do is select an ordered basis of the field extension fq to the m over fq. Any choice of ordered basis will do. The rank distance will not depend on that choice of basis. Okay. Now that we have this fixed basis, let's define this map psi that goes from the space of vectors with entry in fq to the m to the space of n by m matrices with entry over fq. And what this map psi does is it takes an entry in the vector and really extends it as its coordinate vector with respect to this ordered basis b. Okay, you repeat that for every entry and you get an n by m matrix. And let's call this matrix the coordinate matrix of this element V, okay? Now that we have those coordinate matrices, we can define the rank metric, and the rank distance between two elements V and W will just be the rank of the difference between their coordinate matrices, okay? Let's look at a quick example. Let's consider elements in F2 cubed to the 3. Fix an ordered basis of the field extension F2 cubed over F2. Just choose one alpha square, where alpha is the primitive root of this polynomial right here. Choose two random elements, V and W. The coordinate matrix of V with respect to this spaces B will just be 1, 1, 0 for this first entry, 1 plus alpha. Then the second row will be 0, 0, 1 for this entry alpha square, and 1, 1, 1 for alpha, 1 plus alpha square, okay? One can check that the coordinate matrix of W will be given by this. And now that we have those coordinate matrices, we can find the distance between V and W, just the rank of the difference between those two matrices. And we see that the first and last column cancel out. We're left with a matrix of rank 1. So the distance between V and W is 1. Okay, so now that we have a better understanding of this rank metric, we define a rank metric code to be a subspace of the metric space FQ to the M to the N with the rank metric. Okay. So in coding theory, some stuff we want to study are invariant of those rank metric codes. So really properties of those codes that are not changed under isometry. Okay, so isomorphism that preserves this rank distance. And those invariants will give us really nice properties for all applications of coding theory, which I won't get too much in detail. But one of the most famous invariant is the rank distance of a code C. And the rank distance is just the minimum distance from any non-zero element in our code to the origin. Okay. Another invariant, which is slightly more complicated to define and to understand, but which has really useful applications, are those generalized weights. Okay, one way to define those generalized weights is in the following way. So Rav and Jany introduced this definition in 2014, and this definition uses this notion of anticode. An anticode is just a subspace of FQ to the M to the N, where the dimension of that space A is equal to the maximum rank over all coordinate matrices of that space A. Okay. And from those anticodes, we can define the rth generalized weight to be the dimension of the smallest anticode that intersect a code C with dimension greater or equal to R. And those generalized weights really generalizes this notion of rank distance as well, because one can check that the first generalized weight is equal to the rank distance. Now, I don't want you to fully understand what those generalized weights are. They're hard to just grasp. I just want you to know that there are useful invariants of our rank metric codes. Okay, so keep those generalized weights in mind. So if we can find a way, so our hope is to use this theory of q-Matroid to really extract that kind of information, right? So let's look at how can we define a q-Matroid from a rank metric code. So that was defined and found by Uris and Pelican in the same paper where they introduced q-Matroid. And what they did is they choose a code C and choose a generated matrix for that code C. So the row space of this matrix G will just be the code. And remember, for the q-Matroid, we want to define a rank function. Okay, so we define the rank function in the following way. We take a subspace of FQ to the N and choose a generating matrix for that subspace such that the column space of that matrix Y sub V is equal to the subspace V. And then we say that the rank of V is just the rank of the product between our matrix G and our Y sub V. Okay, one can check it forms a rank function of a q-Matroid. Now I want to give you a slightly different way to think about this rank function. I want you to think that this subspace V that we choose selects a collection, so selects a set of FQ linear combination of the columns of this G that we start with, and that the rank of this space V will just be the dimension of the space generated by that set of linear combination of columns. And that should, like, if you think about matroid theory, remember we select a subset of columns of our matrix G. And you can kind of see that Q analog just popping up in here. So let's look at a quick example. We have this matrix G, okay, that generates our code. Let's choose some random, so this G lives in, the entries are in F2 cube, okay? Select a subspace V in F2 to the 3. Say this one, a generating matrix, and we see that the rank of V will just be the rank of G times Y sub V, which if you do the computation will be equal to 2. But another way to think about that is label those columns, column 1, column 2, column 3. This Y sub V, what it does is it tells you select the linear combinations, column 1 plus column 2, and column 3. And if you select those are exactly those vectors right here. And now the rank of V will just be the dimension of this vector space generated by those linear combinations of columns. And that's equal to 2. Okay? So that's nice. We have a q-Matroid associated to rank metric code, but does it tell us any useful information? So let's look at, let's expand a little bit about the theory of those q-Matroids. So just like for matroids, regular matroids, we can define this notion of flat of a q-Matroid. And a flat will be a subspace of Fq to the n, such that any other space, subspaces that properly contain this F has rank strictly greater than the rank of F. And what's nice is if you look at all those flats, the collection of flats, they form a lattice, a geometric lattice, and they fully determine the q-Matroid as well. And so why are those flats useful? Well, remember those generalized weights? So those generalized weight we defined using those anti-codes, really nasty definition, looked hard to find. Well, with my advisor, Dr. Galusian-Larsen, we were able to find that those generalized weights of the rank metric code are fully determined by the collection of flats of the associated q-Matroid. So if you start with the rank metric code C, look at its associated q-Matroid and its collection of flat, then the rth generalized weight of C is just given by n minus the maximum dimension of a flat, such that the rank of the entire space Fq to the n minus the rank of that flat is greater or equal to R.
Can I ask a question from the chat?
Yeah.
Yeah, so Galen's asking if does every q-Matroid have an associated non-q-Matroid? And I think that this means, this is my question as well, was like, if you have this lattice of flats, is that just like the lattice of flats of a matroid?
So since that lattice of flats is geometric, I mean there is a regular matroid that has the same lattice of flat, and I think what you can do is consider if you take, okay, it would be like the matroid where the ground set is just q. So the number of one-dimensional elements. So it'd be q to the n minus 1. But what happens is you kind of like, if you start with this ground set, you kind of identify each, like you get a huge lattice, right? And when you go from that lattice of subsets to the lattice of subspaces, you kind of identify a bunch of subsets together. I don't know, yeah. But I've tried to think about that, like just the fact that this lattice of flat is the same as the lattice of flat of a regular matroid, and still working on it a little bit, and it's really interesting. I find it, and yeah. But so yeah, going back Galen, I hope I answered your question. I don't see the chat, but yeah, so what's really cool about this result is that the q-Matroid is a useful, we can see from this result, it's a useful notion. It's a useful object. We're able to determine some stuff from ranked metric code. Now, one could wonder, can we determine other invariants of ranked metric codes directly from the matroid, the q-Matroid, sorry. But another different question is, where else can we apply those q-Matroids? So far, the main examples of q-Matroids come from those ranked metric codes. And there's actually not much theory next to it, or not many objects next to it that we know of that give rise to this q-Matroid. So it'd be interesting to determine other objects that actually give rise to this q-Matroid and see if those q-Matroids give different information than just regular matroids. And so this is a little reference of some papers. And thank you for your time.
Let's all unmute and thank the speaker or clap react. Then. So yeah, are there any more questions?
So I have a couple of questions.
Yeah.
So if you could go to the definition of the generalized weight.
Yeah.
So yeah, this is just out of curiosity. So you have already said that there is a much simpler way of understanding the generalized Hamming weights in the further slides. But if you just unwrap this definition, this is a minimum over the dimensions of these anticodes, and the dimension of an anticode itself is a maximum over some elements. So I would think of this as a min-max over a set. Now, it's not always, but sometimes a min-max could be written as a max-min potentially over some simpler domain. So something like that, is it known?
So I'm not sure if this is like so if this is a min max, I'm not sure what the max min would be, but I know there's like 4 or 5 different ways to define those generalized weights. And yeah, there might be there might already be like some kind of max min, but just off the top of my head like that, I don't really remember. Yeah, all those definitions are more like nastier, like one after the other. There's like none that are just super trivial, and I've tried to find the easiest way, but you can think about those generalized weights in a variety of ways, and yeah, so there might be something like that.
And secondly, how much work is, how much analogous work is done over q-Matroids as compared to matroids? So for instance, one thing that I could think of is a collection of some algorithmic questions about matroids, for instance, counting bases or getting a stationary distribution on the collection of bases, things like that.
Yeah.
So,
yeah.
So the Q setting, is there something known analogous, or is it all open?
So yeah, I mean, that's those q-Matroids are still like pretty new. So a lot of kind of, especially I'm thinking when you say counting the number of bases, like I'm thinking immediately of like some polynomial out there that tells you, like, if you look at, like, for example, the characteristic polynomial, the tut polynomial of the matroid that gives us all kind of like useful properties and counts a bunch of stuff. None of that is yet defined for q-Matroids. And actually all those bases, all those cryptomorphic definitions too, were just kind of fully determined just like 2 months ago, even 1 month ago, when a new paper about it came out. And so yeah, it's like still brand new, and I think there's a lot of cool stuff behind it. And I think, yeah, a lot can be determined from it.
That was a question I had as well, actually. Like, can you look at like, oh, this is like a Q circuit and that says like this about the rank metric code or something?
Yeah, so yeah, so you can define all the same things like circuits, like bases, independent spaces, and all that stuff. But what's funny is that, you know, those like properties, for example, for circuits, you have like, if you start with a collection of sets in a regular matroid that satisfy those 3 properties for circuit, then you can determine a matroid from it, right? Well, all those properties are not exactly the same when you look at the Q analog. And sometimes it's just not the obvious analog you would want, and you kind of have to like change a little bit. And yeah, it's really,
Whereas like I feel like the rank function is like exactly what you want it to be.
yeah.
Mhm.
Yeah. So that's why they started with rank function and kind of like went from there and try to figure out everything afterwards.
We should probably let the next people start,
Yeah.
next session start. So yeah, thanks everyone for coming. And great talk. I feel less scared of Q things now. Thank all of our speakers.